So I guess you might have already visited this in the previous sessions, but why basically do we carry out statistics, especially in the area of epigenetics? Obviously, um, uh, we would typically want to explore the data and try to analyze and sort of, make sense of this huge amount of data, especially in this particular setting where things are not always terribly clear. Needless to say, you're trying to do this to try and infer any significant differences or any significant association with any phenotype you're observing typically, okay? And with what kind of uncertainty. And as Professor Turner has already alluded to, obviously you've already been discussing the design of experiments to actually achieve this, okay? I guess you've already probably been exposed to this. It is common parlance, at least in the circles I belong in. So I'm not sure how much you subscribe to this point of view. Anyway, but back to serious matters. So typically we look at these sort of classical imprinting studies, looking at parent of origin effects in specific diseases, phenotypes again within families, and not only that, of course, we also look at genotype data. With epigenetics, at least, I mean, I'm not I'm not a geneticist or an epigeneticist myself, but at least the involvement I've had, it appears that there is no specific direct measure of epigenetic marks, but we have a lot of proxy measures. And these are just some of the examples: allelic expression, methylation, or histomodification. Okay. It's always obviously a challenge to assess the validity and reliability of what you're using as a marker. What I'm focusing on, however, in these few slides is how to actually look for associations and how to quantify uncertainty. Because I believe, at least from the involvement I've had in the subject, this seems to be what you typically would be wishing to do with epigenetic studies. Okay, so first and foremost, I'd like to touch upon matching. I'm not sure how much you've touched upon matching already when it came to study design. Needless to say, matching typically, the term matching suggests actually matching our cases with controls in such a way as to control for any potential confounders. Okay, so if there are other confounders that are likely to be associated with the disease of interest, but we are not really interested in quantifying their association, but rather the association of another factor, then we typically go for matching a priori before starting the study to try and eliminate the effect of those confounders. Okay, we can do this in either of two ways. We can actually select a control for each case, and therefore we could have pair matching. Okay, and in that case we can use actually of a specific set of statistical tools if we wish. But what we do most of the time is frequency matching. So making sure that the confounder of interest is equally represented in the two groups, in our cases and in our controls. Okay, so if say smoking is a confounder in our case, then we make sure that at least smoking rates amongst the cases and amongst the controls are similar. All right, and you do that obviously for the number of confounders that you might have. So okay, so that's an illustration of matching for you. Let's say this would be pair matching by definition. Now, again, from my understanding of epigenetics, we typically look for variation between individuals, sometimes even between different types of tissues, or even over time. Okay? So when we look at differences, we typically look at differences between tissues, between individuals, or even within the same individuals across time. But then, in other settings, we might be interested in evaluating correlation between members of the same family, between relatives. Okay, we might also be looking at correlation between different loci within the same individual, or even different alleles at a specific locus. All right, and once again, also between tissues and across time. So I'm going to focus primarily on these two, variation and correlation. Okay. This is, again, trying to sort of set the scene to choose the right tools that we would need for statistical analysis of epigenetic studies. Okay. So what do we have to deal with here? Again, identifying the best study design. We need to think of how to relate the factor to the disease, how to account for other factors. We already discussed this a little bit through matching, and also how to deal with associations between relatives or different family members. Okay? Now, we might have different levels of correlation between individuals and within individuals, which we might have to deal with separately. Okay? We might also wish to deal with the measures of epigenetic marks, both in an absolute level or simply relative between groups of individuals. And what is also sometimes of interest is parental origin. Okay, so in most cases, when we deal with epigenetic studies, we're not looking at huge numbers of people, or we're looking at data which is not normal, as in not normally distributed. I hope everyone is familiar with a normal distribution. So, the sort of, if I had to look at, let's pick up something non-epigenetic, if I had to look at cholesterol levels amongst you, it's likely that I'm going to find very few with very low cholesterol levels, the bulk with something in between, and very few with very high cholesterol levels, giving me that typical bell-shaped distribution. Now, in epigenetic studies, most of the time we might not be dealing with data that follows such a distribution, either because of the nature of the variable of interest itself, or else because simply we have a very small sample size. Okay, and with very small sample sizes, usually we do not assume parametricity. So in most cases, we might wish to explore whether the variable at hand, whether the data we're looking at is actually normally distributed or not. And that's why I'm focusing a bit on parametricity. Okay, so when a statistical test tool is used on normally distributed variables, okay, we usually call those parametric tests. Okay, so the tests we discussed, we haven't discussed many yet, but most of the tests we know, t-test, analysis of variance, etc., they tend to follow a normal distribution. Okay, whilst on the other hand, then we have another set of similar tests that can be used with non-parametric data. Okay, so we need to distinguish we need to actually identify what kind of data we have at hand to decide which family of tests we need to go for. Okay, as we discussed, the more data points a distribution has, typically the more it can approach a normal distribution. Okay, and this we mentioned already. Okay. Yeah, so when we carry out tests for normality, okay, when we get a significant p-value, because this is again sometimes confusing for some people, when we get a significant p-value from a normality test, that means that the assumption that the distribution is normal is violated. So significant p-value suggests non-normality. Okay, so we need to keep that in mind. I think if you can take a take-home message, so to say, any normality test that we're going to use, if we get a significant p-value, that suggests that it is non-normal data. The most popular test for normality is the Kolmogorov-Smirnov, which you probably might have heard about. Okay. Now, this typically performs quite well with large data sets. From experience, I must admit that I find that with smaller data sets, it typically gives me problems. It's very difficult to get non-significant p-value with a small data set. So most of the time with a small data set, the Kolmogorov-Smirnov would basically return a non-normal distribution. The test or tests really that I tend to employ when I have small data sets are the next two. Frankly, my favorite one is the third one in the list. So the Shapiro-Wilk is again a very popular test. It's available in most statistical packages. Okay, and it definitely performs well with smaller data sets, but there is a modification of the Shapiro-Wilk, which is less well known, but equally acceptable for your publications. And it has been implemented in certain packages. So I use it in Stata myself, the statistical package Stata. I'm sure it's been implemented in R. Everything has been implemented in R, frankly. And this typically is, I feel, the best performer when it comes to testing normality for small data sets. But most of the time, what I recommend to my students is to use a QQ plot. And I'd like to demonstrate this if you allow me. Okay, what's a QQ plot? So you might have heard the word transformations, all right? Sometimes we have to transform the data in order to be able to analyze it, okay? I'm showing you just a simple transformation here. If I had to, if I had the equation y equals x squared, if I had to graph y versus x, I would get something like that U shape, okay? Now, the tools I have might not lend themselves well to such a curve. And I wish to convert it into a linear distribution. So what I can do, instead of plotting y against x, I would plot y against x squared. And like that, I get a straight line. I hope this is clear for everyone. I know I hope it's not getting too heavy. Okay, but basically, I'm seeing exactly the same data. But if you notice, the x-axis is labeled differently. In one case, it's the x-axis. In the other case, it's x squared on the x-axis. All right, and like that, I've converted into a linear distribution. Why am I showing you this? Okay, there's a transformer for you. I'm showing you this because the QQ plot is actually a transformation. What kind of transformation? It shows what is a normal distribution typically, the bell shape that we're accustomed to. It transforms it into a straight line. And like that, we are in a much better position to assess how close the distribution is to sort of a nicely perfect symmetrical distribution. Okay? So, for example, the bottom one is less peaked, you might realize. sorry, it's sort of, it's more peaked if anything. Okay, so we get a slightly different, as you can see, QQ plot with two ends going in opposite sides. That is fine. When the QQ plot diverges from that straight line, straight diagonal line, in both directions, what it's suggesting is not that the data is not symmetrical, but that the tails are too heavy or less heavy, so to say, than your average normal distribution. But in terms of symmetricity, which is really what concerns us when it comes to using a parametric test or not using a parametric test, it's still okay. Okay? This is where it's not okay. When we have a skewed distribution. A skewed distribution, as you can see from this graph here, all right, will give us a QQ plot where the two ends diverge from that diagonal line on the same side. That suggests skewness. And that in that case, we should not be using a parametric test. Okay, we should be using a non-parametric test. I can't see your faces while I'm presenting, so I'm not sure if anyone has a question at this point that you'd like to discuss, or else you prefer to just move on. Do I see a raised hand?
Yes, there's a raised hand. I've taken the microphone and I'm moving round.
I was wondering, so you presented the Shapiro-Wilk test and the Kolmogorov-Smirnov test, and now the Q and Q plot. So even if one of the tests is significant and it suggests non-normal data, you would always recommend looking at the Q and Q plot and kind of taking that as your main decision?
So I have to weigh my answer a bit carefully here. I definitely would not recommend shopping around for significant tests, so to say, or non-significant tests. Okay, so it's not the case of trying them all and hoping that one of them ends up as not significant, something like that. But what I'm trying to show you is basically tools that typically work with any data set. And I think the QQ plot usually works with any data set of any size. So that would be that would typically be the first test I employ, at least, if anything, to get a visual idea of normality. Then you can proceed, if you wish, with a formal test.
Okay, thank you.
Okay.
We've got another question coming in as well.
Sure.
Yes. So you suggested that if the data is not normally distributed, that we should go for non-parametric alternatives. And for example, in psychology, we usually do a lot of linear regressions. And
yes.
But under the assumptions, normal distributed data is not one of the assumptions. So would you still suggest to go for a non-parametric alternative?
Now, if you're doing regression analysis, there isn't really an adequate non-parametric equivalent of regression analysis. So in that case, you're probably better off transforming your data. Okay, so I'm not sure if you're familiar with transformations. If you have a non-normal variable, you might wish to use its log or its reciprocal if the distribution improves. Are you familiar with trying to do transformations of variables? A bit like I've shown a couple of slides ago.
There seems to be a general sort of
Yeah.
thing, and generally, yes, we at least they've heard of it, of transforming data.
So it's effectively what I showed a couple of slides back. If one distribution doesn't fit you. Oh, let's look at this one, the skewed one, right? So this variable here, probably, if we had to plot it instead of against x, we plot it against, if we plot, instead of plotting y against x, we plot log of y, for example, it might actually improve. Okay, so it's a bit of playing around until the distribution becomes a bit more symmetrical. That would be best to do if you have, grossly non-normal distributed data and you'd like to do regression analysis. I understand there's an online question.
Yeah, about the transformation. Is it so that you look at the dependent variable only, or also independent variables?
Okay, so there are some very specific situations where the answer would be yes or no. But I think at this level, I would recommend to consider both, unless you're dealing with an independent variable, which is categorical in itself, because in that case, obviously, you're not dealing with it as a normal distribution, normal distributed variable. I mean, if we're looking at gender, for example, that can't be normally distributed. So I think as a general rule, we should probably try to ensure that we've got normal distributions across any data that is used as a continuous variable in order to avoid problems. Okay. Shall we proceed? Okay. So minimize this. Yeah. Okay. Same here. Okay. What I told you earlier. So this is with heavy tails now. Again, the graph is sort of diverging in opposite directions, and that is okay in terms of asymmetrical distribution. As you can see, the distribution on the other side is perfectly symmetrical. So it's okay to use parametric tests. So parametric tests are concerned mostly with the symmetricity of the distribution. Okay. Here you have other skewed distributions. So you see one end diverges only, or both ends diverge on the same side of the line. So that's an indication that it's skewed. And it might either need transformation, as we discussed now, or if you're not doing regression analysis, you can probably opt for a non-parametric test. Okay, so again, I'm trying to do the basics here. So please allow me to insult your intelligence, just assuming zero knowledge. You know what a mean is? Okay, just for us to be clear. So if I had, I don't know, nine babies in a sample, these are their birth weights, that would be the mean. Okay, so mean, average, whatever you wish to call it. Okay, now the mean is important for us to be able to calculate the variance. Now, what's the variance? The variance as a concept is a measure, obviously, of how spread out a normal distribution is. So if I have a very peaked distribution, I'm not sure how familiar you are with, for example, the typical distribution of potassium levels in blood, right? So potassium is a highly regulated substance in the body, and it gives us a very tight normal distribution if we had to look at potassium levels in the population. That would have low variance, okay, as opposed to the example we discussed earlier, cholesterol level, where we would have a much higher variance because it's not as tightly regulated. So the variance is a measure effectively of how spread out the distribution is. So the mean or the average is going to give us the location of the peak, and the variance is going to give us the shape of the curve around that peak. So these two quantities, actually, if you have these two quantities, you could recreate the distribution in effect. Okay, so again, just taking you through the basics. Apologies if this is way below you, but I'm just making sure that we're all on the same track, so to say. If I had the same 10 moms and I had their maternal age, okay, I need to know the average to be able to proceed further with the variance. What the variance does is it calculates the deviations of each mom from the mean. Okay, now those of you who might not be familiar with this might be asking, why are we squaring? The reason why we're squaring is because of that minus sign, okay? So obviously having mums to the left of the mean or less than the mean is going to give us a negative difference, all right? If we have mums on the other side of the mean, so having an age which is higher than the average, that's going to give us a positive deviation. If we had to average the two, given some of them are minus, some of them are plus, we're going to end up with an average of 0, of course, because 1/2 cancels the other. So one way to deal with that is simply to square. And as you know, when you square, minus times minus becomes plus, plus times plus becomes plus. So like that, in a way, we've eliminated the minus or plus, and we can actually get an idea of how far the distribution is from the average. Needless to say, the variance is on a different scale, all right? So if we're looking at years in this case, the variance is going to be at the level of years squared, which is, as I mentioned, we've never dealt with, okay? We can't really work with. So that brings us then to the standard deviation. What's the standard deviation? It's simply the square root of the variance that we've just calculated. So in our specific example, from years squared back to years, which is a quantity we can deal with. All right. Now, what is really a standard deviation? I mean, what's it telling us? You have to believe me on this. So there is such a thing as a mathematical proof that shows that in any symmetrical normal distribution, if I had to take the mean, all right, in this case, the mean is 28 years, somewhere here, and I add one standard deviation to it, and I also subtract one standard deviation, all right? So within this range that I have drawn out here, which is 2 standard deviations wide, I should have round about 68% of my study population. Okay? That is actually what's standard about standard deviation. Simple as that, really. All right. So if if I tell you, you know what, this group of mums had a mean age of 27.8 years with a standard deviation of 4.5. If we had to round it up, let's say it's 28 and 4, just to keep it simple. All right. If I had to tell you 28 plus or minus 4, you know that between 26 years and 32 years, I actually have 68% of my study population. So my study population, around 2/3 of them, were between 26 and 32, right? 26 and 32 years. And I hope that's clear to everyone. So what are we discussing here? We're basically looking at measures of variation, okay, as I promised you earlier on in the session. Now, this is now a bit of a quantum leap. In what sense? From standard deviation to standard error. In standard deviation, you heard me use the term study population. So the standard deviation is something which is describing my study population. And anything I'm saying is simply referring to a characteristic of my study population. But most of the time, if we want to test for differences, especially between populations, then we need to make inferences to the reference population from where I got my study population, all right? And in that case, we speak of standard error. What do we mean by standard error? So I've just said mean maternal age in this group of women was 27.8 years, let's say 28, okay? Now, if I had to walk on stage and present this figure, someone from the audience will probably ask me, how sure are you of this estimate? Do you think it's actually precisely 27.8 years? In other words, if I had to repeat your experiment, will I get exactly the same figure? If I had to actually measure all the women in your population, not just the study population that you picked out, will I get the same figure? And obviously, we know that it's not the case. All right, I need to allow for a margin of error around my estimate. Okay, and that's where the standard error comes in handy. So the standard error is a standard unit, if you wish, of the margin of error around our estimates. Any statistic can have a standard error. All right, we could be talking of an odds ratio, a risk ratio, a mean, like in this situation. Okay, but it basically gives us a range of values wherein we expect that statistic to be if somebody had to go out there and actually measure the whole population, all right, millions, whatever, past, present, and future. If anyone had to repeat the study, his or her mean should be within this range of values. Okay, so I'm alluding here, I'm building towards something that you probably know already, which is the confidence interval. Okay, so again, sticking to our population, we had a standard deviation. I don't think I showed you the formula here, but the standard error is, sorry, it's not coming up on the slides. So standard error would be the standard deviation divided by the square root of the sample size. Okay, so I don't think I can add it through a notation. Okay, so you basically have, yeah, oh dear, SD over square root of n to get that 0.4 of a year, right? But what's that 0.4 of a year? That 0.4 of a year allows us to describe what we call a confidence interval. So I'm going to use the same methodology I've used before for the standard deviation, but I'm in a completely different dimension here. I'm not talking about the distribution of a specific quantity, in this case maternal age, in my study population, but I'm talking about the potential variation of mean maternal age in the reference population from which or on which I'm carrying out my study. Okay, so if my mean is 28, all right, and I'm saying I've got a standard error of 0.4, what that means is that I am, follow what I'm trying to say, 68% sure that the real mean maternal age out there, if someone had to actually, measure all the mothers out there, we will get an average which is somewhere between 27.6, so I've subtracted 0.4 if you realize, and 28.4, I've added 0.4, all right, subtracted 0.4, added 0.4. Okay, so then again, have you ever heard anyone talking about being 68% confident? Probably not. Okay, what figure do we usually hear associated with confidence? We usually hear 95% confident. Now, how can I be more confident, would you say? So with one standard error, up and down, I can be 68% confident. How can I be 95% confident? Okay, hopefully you're following what I'm trying to say. I mean, feel free also to use the chat, those of you who are online and wish to ask any questions or discuss. All right. In order for me to be 95% sure of hitting the real mean out there, I probably have to go for a wider range of values. I hope you agree with me. All right. So in fact, I would be taking almost 2 standard errors up and almost 2 standard errors down. So almost 4 within the whole interval in order to be 95% sure of covering that real mean maternal age out there. Okay? In reality, we have to be precise. What we would add and subtract is 1.96 standard errors, not exactly 2, a little bit less, 1.96. Okay? So if I add 1.96 standard errors, subtract 1.96 standard errors from the mean that I have estimated, then I will get a 95% confidence interval. So I'm not sure if I have a slide demonstrating this. Yeah. So this, let's use this actually. I think this is good because it's actually taking us into significance testing slowly. So again, same example. I know it's not an epigenetics example, but I hope it's something. I know many of you come from an obstetric background, so I'm hoping that this is something that you feel familiar with. So let's say I'd like to look into birth weight by gender. All right? How can I do that? I have a sample of babies. Obviously, not all the babies I've seen in my career or all the babies that I will ever see. I have a sample. So again, some formulas have not shown up here. Okay, I have, if I'm not mistaken, 78 males. Okay, so you could actually work it out again. So I have 78 males, the average of which is 3469 grams, and 40 females, the average of which is 3190 grams. Okay, I've measured my standard deviation, 645 in the case of males, 497 in the case of females. And having also the n, if you recall, I can actually work out the standard error as well. All right, and the standard error is 73 in the case of males, 78.6 in the case of females. So what have I done to get to that answer? I've taken the standard deviation, let's think about males, for example, 645, and I've divided by the square root of my n, which, even though you can't see it, it's actually 78. Okay? Now, why am I doing this? Because I'd like to establish if somebody else had to repeat my experiment, if somebody else had to actually do it on all male babies out there, they should get an average which is within my confidence interval. Okay? So indeed, if I take the mean, 3469 grams, and I add almost 2 standard errors, which is 73 grams, then I would get that 3612. If on the other hand I subtract 1.96 standard errors, I would get 3326. Within this range, 3326 to 3612, I expect that if anyone should repeat the experiment, they should get a mean birth weight, which is within that range. All right? And I'm 95% sure of this. So frankly, if you get a result which is outside, I can say that you're within the other 5%. No, seriously. Okay, we can never be 100% sure on statistics. But 95% sure has been accepted as reasonable within the scientific world. Okay, now I'm going to pose a question to all of you to see what your understanding is of confidence intervals. Given the figures you are seeing in front of you, can anyone tell me whether we can consider females as having a significantly different mean birth rate from males? Any takes?
Can you repeat the question?
Sure. So given the figures you're seeing in front of you, can you decide whether there is a significant difference in mean birth weight between male and female babies? Going for it, Annalena.
There is no significant difference because the confidence intervals overlap a bit.
Wonderful. Thanks, because you gave me the incorrect answer I was after. And I will try to explain why. So, Annalena made a correct observation. The two confidence intervals indeed overlap. All right? So as you can see, females, for all intents and purposes, the confidence interval we gave for potential values of mean maternal age in females goes up to 3,344 grams, whilst that for males starts from 3,3 to 6. So we have a bit of an overlap between the two ranges. But what I haven't told, and maybe I was a bit unfair when I posed the question, is do we expect the same chances? Basically, no, so let me rephrase this. What are the chances of obtaining any specific value within a range, within a confidence interval? If Annalena had to repeat my experiment, most likely she has better chances of getting a mean birth weight for males, which is closer to my estimate than to any of the two extremes. You follow what I'm trying to say? So the probability, the chances of getting a mean birth weight, which is different from mine, sort of peter out, all right? So they diminish the further away you go, because after all, it's a normal distribution, remember? Okay? So the chances are much higher towards the center of the distribution than towards the end. So in fact, what happened to Annalena is that she was punishing herself too much, if you wish. Because what we do usually to do a significance analysis in this case, we would compare the mean of one group with the confidence interval of the other and comment on that overlap. So what do you think now, Annalena? Do you consider them using this method? Do you consider them as significantly different?
I need to check the numbers again.
Mean birth weight for males.
Yeah.
Does it overlap the confidence interval?
The 3, 4, 6, 9 is not covered in the confidence intervals of female.
Indeed.
And other way around as well. So they are significantly different.
And that is the right answer, actually. Thank you, Annalena. Sorry for picking you out again, but just to continue in the same vein. So that is indeed the correct answer. And if we had to carry out a significance test on this data, all right, we would actually get a p-value which is less than 0.05. I hope you're familiar with the range of p-values, right? A p-value of less than 0.05 usually suggests that we have a significant result. Okay. So we move on. A wider confidence interval, what does it suggest? A very wide confidence interval. It suggests a lot of variation. Okay? So I know this is a bit of a cartoon, but actually the message is correct. All right. If I see a mean or a statistic with a large confidence interval, then I can't really comment whether we're different from that mean or not, because we know that the confidence interval is so wide. Okay. So, the guy at the end with a mustache could actually say that he is significantly different from the one next to him with the open mouth, because his mean falls outside the confidence interval. On the other hand, he can't say whether he's significantly different from the red guy, the red column, because the confidence interval of the red column is so wide. Okay. Now, this typically happens either because there's a lot of variation in the data in the first place, but most commonly is because there is a small sample size. Maybe you're carrying out subset analysis within your data and you've got one group which is really small. Okay. So I come from Malta. Sorry, I didn't introduce myself actually earlier on. And this is something that happens to us a lot when we're carrying out international analyses. Okay. That we get wide confidence intervals because of small data sets. This, I hope, should be something you're familiar with. What is a null hypothesis? Okay, so it's what we presume to be true until statistical evidence is showing that it's not, or it's unlikely actually, with a hypothesis test or a significance test. Okay, and obviously then, if there is a null hypothesis, there is an alternative hypothesis. Okay, so in the little example we did, this would be the null hypothesis. There's no difference in birth rate between male and female babies. This would be the alternative. There's a significant difference between male and female babies. Okay, I know that. Well, we started late, so I hope I can afford to steal a few minutes from the next session to complete the few slides that we've got left. So one test that we use is the unpaired t-test. So the unpaired t-test allows us, the example we just had, right? Birth rate by gender. Two groups, male, female babies. And then we've got a continuous quantity. We'd like to check whether it varies between the two groups. It's precisely the same setting, all right? In that case, we would employ the unpaired t-test. I'm not going to show you how to work out an unpaired t-test because nobody does statistical testing by hand these days, at least. Okay? But what is important is that when you're using your statistical package, whatever it is, you choose the right test. All right? So if I'm testing a quantity, whether it varies between two groups, then I would employ the unpaired t-test if I am convinced that the data is fairly normally distributed. What happens if I have more than two groups? So, I don't know, I'm looking at 3 different ethnic groups, and I'd like to assess whether my epigenetic mark varies between these 3 different ethnic groups. Okay? Then I would have to employ a modification of the unpaired t-test, which is the analysis of variance, or ANOVA. In some countries, it's also known as the F-test, because it gives you what they call an F-statistic. But ultimately, all tests that we're looking at give us a p-value, and that's what we really need to know. Okay? So the p-value is the lingua franca, the Esperanto, call it what you like, of all the statistical tests that we can use. Okay? We always get a p-value. That's what's important for us. What's also useful for you to know, especially in epigenetics, is how to compare between separate groups. So let's say I have 5 different groups, which I'm comparing against each other. So I would use the ANOVA test to compare between those 5. But what the ANOVA or F test will tell me is that the mean of the 5 groups is not always the same, but it's not telling me which one is different from the others. Okay? To do that, most of the time we go for what we call pairwise comparison, group 1 with group 2, group 2 with group 3. But when we do that, that is not exactly statistical good practice. Okay? So if you just try to test with an unpaired t-test, each combination of two groups, that is usually not considered good practice. It's actually called data dredging, because it's like you're trying to fish out a significant p-value in some way or another. All right? The correct way of doing it is to carry out ANOVA with what we call post hoc tests, such as the Bonferroni. All right, and the Bonferroni is actually the right. It's an additional test which we usually do with ANOVA that then gives us the pairwise comparisons, and it actually adjusts the cutoff p-value in reality. That's what's happening, but it's happening in the background. You don't need to bother too much about it. All right, so when we need to compare different groups against each other, when we have more than two groups, we don't use the t-test to compare each pair of groups, but rather we carry out ANOVA with a post hoc test, such as Bonferroni, for example. I think the American-speaking world calls it alpha splitting, as opposed to Bonferroni, but it's just effectively almost another name for the same kind of adjustment. Now, let's imagine we did our normality test, but the data is not normal, all right? So I'm going for a non-parametric test, okay? Again, each parametric test amongst these that we're going to discuss has a non-parametric equivalent. In the case of the unpaired t-test, if my data is not normally distributed, that is, it's skewed data, then I can employ another test known as the Mann-Whitney U-test. Or again, in some places, it's known as the Wilcoxon rank sum test. It's actually the same test. All right? In the case of ANOVA, if the data is not normally distributed, then I would employ what is known as a Kruskal-Wallis test. I know they're difficult names. I'm sorry, I didn't name them myself. I would have called them Mickey Mouse and Donald Duck if it were, but we have to live with it. All right, so the Kruskal-Wallis test, again, if I need to do pairwise comparison between the different groups, and I'm carrying out an analysis of like what, 5 groups, then I should use post hoc testing. And in this case, the post hoc test to use is known as Dunn's test, as shown on the slide. Again, I'm afraid not all statistical packages do Dunn's test, but I think GraphPad Prism does it for sure. R does it as well. Again, I think Stata does it too, but I'm not sure about SPSS. Now, there are other tests, okay? I'm just going to mention them to you, and maybe then you'll have like the opportunity to read up a little bit about them. When we have really small variables, all right, really small data sets, you know, like, I don't know, 5 individuals, that sort of thing, and we'd like to test for differences between groups, then even the non-parametric tests might be stretching it, all right, if we have really small groups. And these are 2 techniques that are used with very small groups. One of them is known as the permutation test. I know I've given you the official definition there, but I would really suggest that you seek assistance if you need to do these tests, or at least you might wish to read up a little bit more on them. There's also something known as empirical based. We haven't spoken of Bayesian methodology in this session yet. I'll come to it in the final slide. But again, it's one technique that is employed with very small data sets. Okay, let's move on to correlation because I'm conscious of time. The most commonly used test in correlation is the Pearson correlation test. All right, so if we have two continuous variables between whom the relationship is linear or is being assumed to be linear, then we would employ the Pearson correlation test to assess whether they are actually associated or not. All right, I don't know, maternal age, sorry, or rather gestational age with weight of the baby at birth. All right, that would be, I would use a Pearson correlation test to check that. All right, or the epigenetic marks versus the penetrance of a specific disease. Okay, again, if there's a linear relationship between the two, you would use the Pearson correlation test. On the other hand, if again the distribution is not exactly normal, is not nice and symmetrical, or it might be on an ordinal scale. Okay, I'm not sure if you're familiar with ordinal scales, so they're not precise measurements, but it would be maybe 1 of 5 You'll find these in any statistical package that you use. They're obviously the staples. I hear a question, but I can't really hear.
No, Neville, you froze for a minute or so. Can you just repeat?
I'm aware. So yeah, I was just saying that if we have non-normal data or we have ordinal data, and I illustrated the difference between continuous and ordinal by using the age example, age versus age group, all right, highly restricted variation, then we would use Spearman correlation test. I hope that's okay. I'd like to move on to another typical analysis that we carry out in epigenetics, which is outlier analysis. Okay, what is an outlier? It's basically individuals' values that seem to be out of the norm. Now, how do we define an outlier? In statistical methods, there are various ways how we define outliers, but at least from the literature I've come across, it appears that the relatively accepted definition of an outlier in epigenetics is a value that is 3 times or more than 3 times the interquartile range. So what's the interquartile range? You have a box plot in front of you. Each of the horizontal lines marks a specific landmark in the data set that you're analyzing. So if these are, I don't know, people, okay? No, not people. Let's say, I don't know, levels of something, okay, of hormone X, okay? So it clearly shows that the distribution of most of the distribution lies between around what, 150 and 600 maybe and 30, I don't know. Okay, those are the top and bottom short lines. Then we have the horizontal lines in the box itself. The line in the middle is the median, or what we could call the 50th centile. So if I had to rank all these values in order, the 50th centile, the guy in the middle, is the median, that horizontal line cutting across the box. The top limit of the box is the 75th centile. The bottom border of the box is the 25th centile. What is the interquartile range? It's actually the distance between the 25th and the 75th centiles, all right? Or the first quartile and the third quartile. That's another term that we use to define this. So in our case, what's the interquartile range? It's roughly what, 350, and then the other value is maybe 480. Okay, so the interquartile range is 480 minus 350, 130 roughly. So those dots at the top that are being marked as outliers are more than 3 times that amount, all right, 130, away from the median. Sorry, away from the 75th centile, apologies. All right, so they are more than 3 times that difference from that top border of the box. And that's how they're defined as outliers. Now, these outliers, obviously, in epigenetics, could be interesting for investigation, of course, to try and find what's different for these individuals as compared to the others. Okay. Now, sampling, I'm not sure if you've touched upon sampling. I'm really exceeding my time here, but one way of addressing again certain confounders is to address it through stratified sampling and make sure that the different groups are well represented. In some cases, we even oversample. Okay, so if we have a group which is likely to be underrepresented in the population where we're sampling, we might wish to oversample that specific group. Okay, and then we can apply weights afterwards. This is typically how we make survey data more representative of the population from which it's being sampled, okay? Because obviously people don't just respond as we wish them to, okay? And we do get some groups in the population that are more willing to engage and other groups that are less willing to engage. So if we just analyze the data as is, it's likely that we're going to get a biased, non-representative picture of the population. But if we take on board, if we know how many we should have got from each subset, all right? So when we carry out surveys here in my department, for example, we usually stratify by age, sex, and locality of address. Okay, we know how many we should be getting from each of these pigeonholes, if you wish, all right, that are defined by age, sex, and location of address. If we get less than what we should have got, we can apply what we call weighting and give them a bit more, allow them to influence our results more. The few that we have captured would have so if I should have got 200, but I got 100 from a specific group, then I would allow them in the analysis to represent 2 people each. On the other hand, if in another group I should have got 200, but I got 400, I would allow each of those individuals to contribute half a person each. And this is called weighting. And like that, we can make our data come closer, more representative of the population from which we sample. Obviously, we need to know what distribution is actually available in the population in order to be able to do this. All right. And again, I guess such analyses are obviously useful also for epigenetics. Yeah. Anyway, I'm touching very, very briefly on regression. We mentioned it earlier. Most of the time, one technique that is used in epigenetics is known as logistic regression. You might have seen it used elsewhere. Okay, logistic regression is basically looking at an outcome which is binary. Yes, no, having the disease, not having the disease, dying or remaining alive. All right. The outcome, the dependent variable, is therefore a binary variable. Okay? In that case, we apply logistic regression. Here you have an example. The beauty of regression analysis is that it allows us to analyze against multiple independent variables, multiple risk factors, adjusting for the effect of each other. Okay, so if you look at this table, which is looking at risk of history of anxiety, one cannot argue that females are more at risk of chronic anxiety in Malta, this is Maltese data, because females live longer. All right? No, because it's been adjusted for age. And therefore, what we're looking at is the effect of gender free of any confounding effect of age. All right? So one way to deal with confounders actually is to carry out regression analyses, multivariate analysis that allows you to tackle more than one risk factor at once. Last slide, promise. There are other techniques. I'm just trying to pick on the main ones that you encounter in the literature. Bayesian statistics, we mentioned it earlier. Don't panic when you see something which is analyzed with Bayesian statistics. What you need to know is that rather than start from a null hypothesis, Bayesian statistics starts from a prior position. All right? So sometimes they get what they believe the result should be, so to say, where the significant difference should be, and then see whether the data they've collected supports that prior position or not. So the starting point is a little bit different with Bayesian statistics. The endpoint is the same. All right, we're going to get significance with p-values, etc. We're going to get confidence intervals, which they call credible intervals, just to be different, but you interpret them exactly in the same way. That was the last slide. Sorry, Professor Turner, for taking too long.
Well, thank you very much, Neville, for what was relatively heavy for the statistics, but I think for everybody, going over everything again. And I think most of us we've probably seen at some point that, but for some of us, and I'm not looking at myself, it was decades ago. So I think it's just all the points that we needed to have brought back to us. So I'm going to ask anybody if they've got questions. We've had questions already as we went through the lecture, particularly on the QQ plots. But are there any other questions we have on this? Is there anybody on the online who has a question about it?
Annalena.
About ANOVA and the POSOC tests. So what I've learned to do is to then just change the reference category. And if I understand correctly, that's actually what you say, that's not the correct way to do it.
No, wait. That is one way of dealing with it. If you're only interested in comparing against a specific category. Okay, so let's say we're looking at expression of something by smoking. Okay, so you've got non-smokers, or rather never smoked, ex-smokers, occasional smokers, daily smokers, 4 categories. Okay, if you're interested in comparing every group against one of them, so for example against the never smoked, then yes, what you suggested is okay, because they're going to be compared against always the same group, all right, against the never smoked. But if you're interested in comparing daily versus occasional versus never, ex-smokers versus daily smokers, all combinations, then I would use Bonferroni. Okay, so what you suggest is correct, but you're sticking to one specific reference category.
Okay, great, thank you.
Okay, thanks for that.
Okay, so all that's left for me to do is to say thank you very much to Neville, who actually, if you followed the tweets, there were a whole bunch of tweets all about that lecture. Some of your illustrations, they really got a bit of a following. So thank you very much for actually making statistics treatable. And I think you heard the round of applause that you got.